Hello, Assalamu alaikum. Good afternoon. I hope you all are fine. Today we have the fourth day of the webinar, Optical Forces on Atom. Our guest speaker, Sir Dr. Saif, is here with us. So please, sir, join us, and the stage is all yours. Thank you.
Well, Assalamu alaikum. Today it is the fourth webinar of our 5 webinar series. I'll start with with thanks to Professor Dr. Iqbal Chaudhry Saab, Coordinator General of Comstech, for his personal interest in this book and also his invitation to present this series of webinars. At the same time, I should mention that there are many messages and many students, many researchers, colleagues, they want to have the book purchased. So I would say that you should get this book from the publishers, or you can contact me so I can also arrange a book for you. So, we start the discussion with this small. So this is the layout of our today's talk, that we shall be talking about optical forces in macroscopic quantum systems. So just a quick summary. We have this first few graphs from our previous discussion, first webinar, when we were talking about radiation pressure. And the first evidence of radiation pressure was coming from the work of Peter Arpian, where he was pointing out that the comet tail is in the opposite direction to the sun. So this was a simple observation of radiation pressure. So it was not really connected with radiation pressure, but this was an observation. So later there was a lot of work after that, some fiction, some real scientific. And first attempt to measure the radiation pressure force was made in 1901, where it was connected with the intensity of light. So this was the first mathematical proof that radiation pressure occurs. Something which is very interesting, fascinating for us, that why we don't feel radiation pressure while we move ourselves. So this requires a comparison. For example, that if we think of a dust particle, which is of the size of a 1 micrometer diameter and mass of 10 to the minus 15 kg, it would be experiencing the radiation pressure force coming from the sun radiation, which is equal to 3.3 10 to the minus 18 Newton. So it is the amount of radiation pressure experienced by this particle. But at the same time, the same object would experience a 10 raised to the minus 14 Newton force from the gravity, which is 5 order of magnitude larger than the radiation pressure. So that makes it understandable that the gravity is so strong that we ourselves don't feel radiation pressure and the things around us. But this radiation pressure is very useful in space in making the shapes of different nebula and various different cosmological objects. So this is useful in defining, making, developing some real useful tools, just like our latest nano satellites, which are used, which are propelled by the radiations coming from the sun, basically. So this is one interesting application of radiation pressure force in outer space as well. Okay, in our laboratory experiments, we can experience radiation pressure force, and we can use in, for example, cavity arrangement. We have various different kind of cavities, and the simplest one is where we have two mirrors, and with one mirror with a lesser uh, reflectivity has ability to let the field come inside. So now, if the field is inside, is in between two reflecting surfaces, so this makes a simplest form of a cavity. Now here we shall see that the radiation which are inside, they may exert force on the walls. And there is a very simple requirement for the field to survive inside the cavity, and that is that the length of the cavity should be integer multiple of half of the wavelength. So in that sense, only that or those radiation field would survive which have their wavelength integer multiple to the half of the which are the length is integer multiple to the half of the wavelength. So this becomes a simplest relation we can understand. If the end mirror are made thinner and thinner, they are made lesser and lesser in weight to the limit that the radiation pressure is sufficient to move the end mirrors. And that is something we have in mind. So if the radiation pressure is large enough that it can displace the end mirror, so then something interesting may happen, and that is that with the movement, radiation pressure based movement of the mirror, the length of the cavity would increase. As the length of the cavity is increased, the relation or the requirement of the relation that the length should be integer multiple of wavelength is no more fulfilled. And once that requirement is not fulfilled, so the field disappears. So this is something which is quite interesting to note. As soon as the field disappears, there is no force coming from the radiation, so the end mirror would try to come back. So this is something which we have in laboratory experiment, a very good way to experience the radiation pressure. Now, this simple arrangement gives us some basic understanding, and that is, okay, this is a schematic diagram, a schematic diagram for this kind of systems. So we have the radiation trap between the two mirrors due to the radiation pressure. The end mirror may move and it may start observing a harmonic oscillator and motion. What comes as a basic understanding about this radiation pressure based cavity? We can summarize this in few words that uh, when light comes in the cavity and exerts force on the mirror, on the end mirrors, it displaces the end mirror because the end mirror is so thin, so light, the radiation is sufficient to move it. As soon as the position of the mirror is changed, the amount of radiation inside the cavity is reduced. So this is the back action of the mirror. So due to the movement of the mirror, the radiation amount of radiation inside the cavity is changed. The position of the mirror changes and varies the radiation pressure, thus introduces the cavity effect as it modifies the radiation pressure force. So this becomes the cavity effect that the movement of the mirror is now going to alter the radiation pressure force. So then we observe that this mechanism is something which is very much closer to the nonlinearity of the medium. So the radiation pressure force and resultant movement of the end mirror. So the change in the radiation pressure force and the resultant movement of the end mirror acts as a nonlinearity of the electromagnetic field. So this nonlinearity is very much the same as that we observe coming from the medium once light passes through this. So if we have a nonlinear medium and light passes through this medium, so it experiences the same changes. And this way we are in a position to simulate nonlinearity of the medium as a field observed while interacting with the medium. So this mechanism, so this arrangement in which we have radiation pressure force moving the end mirror is actually simulating a scenario where we have electromagnetic field passing a medium. So this movement of the mirror is, in a sense, simulating a acting like a medium now. So it is an artificial medium which we can think of. So same effects would be seen. Now, so if we have understood this thing, so all what we have been doing with the medium can be done with the optomechanical systems. This arrangement is on a large scale. This is a large system now. So this is something which is quite fascinating. So if we calculate the momentum provided by the field, so we can have a very simple understanding. So the end mirror may observe a momentum change of 2E by C, and then this momentum change occurs once the light completes one cycle between the two mirrors. It goes from one mirror, reaches the other mirror and comes back. And that time is 2L by C. So this introduces a force which is exerted by the field over the end mirror, and that is delta P by delta T, and N becomes the number of radiation field photons. How many radiation field photons are building the field. So this makes the radiation pressure force experienced by the end mirror. We can take this to define the potential of our seen by the mirror, and that is a force multiplied by the displacement, which is covered by the mirror. So due to the radiation pressure force. So this will be the potential energy associated to the moving mirror due to the radiation pressure. We can write in a quantum mechanical way by writing n as an operator expression A dagger A. So this makes a quantum mechanical potential for our n mirror scenario. So this understanding helps us to write Hamiltonian for this system, which we write very easily. So this Hamiltonian is composed of terms, which is it is the cavity field which is inside the mirror, inside the cavity. This is mirror, end mirror, which is moving due to the radiation pressure force. And then we have this cavity field, cavity mirror Hamiltonian coming here. And if there are some noises or some decays, so that we can associate as well later as CL in the form of CL. So this becomes a very interesting thing. We can write in this way. Okay, so this is the mathematical description. If we want to write or not, if you want to remember this or not, don't worry. So there are various different experiments which offer various different kind of optomechanical setups. For example, we can develop this optomechanical setup by using micromirrors, or we can use micromembrane, or we can use microtoroids, and this optomechanical cavity system which we're talking about right here based on end mirrors. And there are other arrangements as well. For example, we can develop optomechanical setups using nano optical fibers. We were talking about nano optical fiber even in yesterday's webinar. So these optomechanical setups can be developed in various experimental arrangements. Now, very popular example of this moving mirror cavities is coming from the gravitational wave detectors like LIGO. Here we also have the end mirrors which are moving due to the radiation pressure force. This is a good example of that. We can extend this simple system by introducing some additions and make them hybrid optomechanical system. For example, in this simple optomechanical resonator, we can add nano nanoparticles, we can add multi-level atoms, we can introduce bosons and condensates. And with the help of this hybrid optomechanical system, we can make many newer devices and applications, such as we can, as I was showing, we can have gravitational wave detectors, we can have uh, 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 optical tweezers. We have been talking about this earlier. We can have optofluidic devices for biological sensing, single atom transistors, novel optoelectromechanical devices, and single phonon detection, and many more, such as we can have quantum memory setups and so on. Okay, now when we want to understand the evolution in this optomechanical system, so in the most simplest scenario, if we don't have the field up here, so we can think of that the end mirror is performing harmonic oscillations. So if we observe that, if we calculate that harmonic oscillation dynamics, we would be seeing it is making a kind of circle in the phase space. But as soon as the radiation pressure comes, the end mirror is observing some external forcing, which is periodic, and that periodic forcing on the mirror modifies its dynamics. And what we see, the modified dynamics is very intricate. It's making many interesting um, shapes in phase space. So by changing the initial position of our mirror, we can develop various different kind of phase space appearances. So these are the phase space appearance of this our end mirror. So uh, underneath, we have a very simple arrangement if you want to compare classically. So we have one mirror which is oscillating. So it is like a pendulum which is performing harmonic oscillation. And then we have field which is coming and going, applying force and no force. Once it is there, it applies force. When it's not there, it doesn't apply force. So it is again a kind of oscillator. So then it is as simple as two oscillators which are oscillating independently, and at sometimes they interact and exert force on each other. So there's two pendulum couple dynamics. So in the two pendulum couple dynamics, we find the system is going to be four-dimensional, and it is going to be a big phase space, and that due to the coupling between the mirror and the field, we should be finding a complexity. So this discussion of higher dimensionality, when we have the coupling available as well, meet complexity or complex dynamics. So without going into the detail of complex dynamics, which is very good part of my book is dedicated to that, I'm simply showing how the picture changes. Because if we have only harmonic oscillator, that will be making a circle in the phase space. Fine. But as soon as the other pendulum comes in, as soon as there is an external agent which is applying force periodically, the evolution is going to change, modify. And that we have this modified picture is quite fascinating. And this picture will change whenever we have the initial momentum changed, initial conditions changed. So this is making our system, if I present it more technical way, it is a complex system or a chaotic system. So this chaotic system is going to be having this shape. Okay, when we are talking about hybrid optomechanical system, so hybrid optomechanical system can be made by introducing atoms in the field in the presence of the moving mirrors, or we may use some membrane, as I was telling, or we can have some nanoparticles or even living objects. So any object appearing in this arrangement of optomechanics will make it hybrid optomechanics. The first thing is that previously, if it was a two pendulum system, which are two pendulums are moving simultaneously and applying exerting force on each other whenever they interact, we have another system entering into the discussion. So in the most simplest scenario, it is a six-dimensional system now. So we shall be requiring 6 dimensions to define about this system and write it. So uh, uh, it is going to be a complex dynamical system right from the beginning. So this we can understand. Okay, if I make the phase space diagram for this hybrid system, it will be different from our uh, uh, simple optomechanical system, where we were seeing very good symmetric periodicities, but now we see okay, these circle are showing resonances, and these dot points are showing random dynamics. It simply conveys that if we have our, because this is position and this is momentum, it simply conveys that if I start my membrane or my end mirror with initial position somewhere in the circle, it will always be ordered dynamics. It will always experience periodic dynamics, even though the external forcing is there. But as soon as our initial condition, which is picked up for our and mirror, is coming somewhere in this stochastic region, so then the ordered dynamics is disappearing. This is the first thing. So the system, our end mirror is going to present itself as a disordered system. So this is what we learn from these diagrams. In a sense, these diagrams are very useful because beforehand you have a very good understanding about all possible initial conditions which would be giving us periodic or order dynamics, and all other kind of initial condition which will take us to disorder dynamics. This is the message coming with it. So this discussion is useful because if we place a quantum mechanical system, if we consider our N mirror a quantum mechanical system, we have this or we have the cold atom as quantum mechanical system, it simply means they have appreciable de Broglie wavelength. This is the simple understanding once we say that it's a quantum mechanical system now. So what we really want to mention or say that this object is now going to have an appreciable de Broglie wavelength. So as soon as our N mirror is having a de Broglie wavelength bigger than the size of the mirror, or our cold atoms which are stored there, making the system as hybrid, they have their de Broglie wavelengths compared larger than the size of the atoms or condensate, and comparable from our yesterday's webinar, we were knowing that this de Broglie wavelength should be comparable with the optical wavelength. So then they will be observing the periodic effect of the light. So then what we see, now this is interesting, that as soon as we think our object is a quantum mechanical object, so this movement of the N mirror in the presence of the field is going to modify the distribution of this object. If we think that our atoms were moving, if they were not quantum mechanical, they were just moving following Brownian motion, so the dynamics would have been a Gaussian dynamics, like Brownian motion. So we know it's a bell-shaped Gaussian distribution is always there. But as soon as we introduce the quantum mechanical understanding, associate this as a quantum mechanical cloud, so then the distribution changes and it drops down exponentially. So that means that now our quantum mechanical object is localized only to a very small region, and outside the region it drops down exponentially. So it is a change in the distribution of this. The reason, the effect of that change, the distribution comes in looking at the momentum behavior as a function of time. So on this vertical side we have time, and here we have a momentum. So what we see that, and this is about the mirror thing. If we have a mirror, which is a quantum mechanical object, it's undergoing, experiencing the periodic forcing coming due to the optical field radiation pressure force. So then, in spite of repeated kicks on the mirror, it will stay localized. So it will be observing a momentum state, which is very dominant because it is an exponentially localized distribution. And this is going to show a repetition in as we move in the time. So there will be a particle. So it will be a collective dynamics of the mirror in the form of quantum mechanical object, and it will be showing a this a localized dynamics. Okay, what would be if our system is not quantum mechanical? If our end mirror is not quantum mechanical and it's experiencing external forcing, so then we observe that the dynamics should have been that gradually, as we let this interaction goes on, the mirror would be observing a dispersion. That means if we have a if we have it, we can think of a tuning fork and we just knock it again and again, it will be having its dynamics over larger and larger space. So that is seen up here. If we enter into the position space, so then we see that in position space, the system is going to repeat itself at periodic intervals. So this is space and this is time. So if we have our initial condition somewhere here at time t equals 0, so then as we move in time in the presence of the kicks coming from the end mirror, this distribution will be staying localized for forever. So this is something which we shall be experiencing up here. Okay, so this is we name it as a time crystal because this crystal appearance will stay only in time. So if we switch off this time, if we switch off the field, if we don't have the optical field present and kicks available on this end mirror, so it will not be displaying any localized dynamics, localized distribution. It would be just a harmonic oscillator. It would be just following Brownian motion, Brownian dynamics in its description, which is very broad. But here we talk about very centralized and following a exponentially decaying distribution. So it is like that. If we talk about the condensates which are available in this system, so we shall see that in the dynamics of the condensate is also going to follow this exponentially decaying behavior. And if we look at the space-time dynamics, so then we see that it is momentum and time dynamics. We see that there are some particular momentum states which are going to survive, and they will repeat it themselves after some intervals in time. So this is something we say as localized. So there is momentum states which are going to survive, and rest they would not be. And this can also be seen in this position space, and we shall see that even in the position space, this initial distribution is going to first modify and then going to be appearing as exponentially decaying and survive. Okay, now these systems, which we say as large-scale optomechanical system, they're quantum mechanical systems, they can be used to study various different aspects. They can be used to study various different characteristics. And we can apply them, for example, to develop quantum storage devices, and where we can have high storage efficiency. We can use these systems as optomechanical systems to develop optical switches and transducers, which are very useful for quantum information. We want to send information from one system to another end. And then we can also use this system to develop transparencies and controlling speed of light. And they can be used for slowing the light or making the faster than speed of light. And here I will close my present webinar, and I am very much there to answer any questions. So these topics, which are about the macroscopic quantum systems, experiencing experiencing optical forces, are also subject of my book.
Thank you so much. So first we take question answer sessions from physical participants. So if you have any question, please let me know. Where's the वो कहाँ चला गया? Mic.
So I have a question, as you have mentioned about the hybrid optomechanics. Can we use these optomechanics to design the detectors which detect the Higgs bosons or the muons?
I was presenting these optomechanical systems, and I was mentioning that they have their role in developing gravitational wave detectors. So there is something which is one application of optomechanical systems, and in detecting particles coming from space. So there can be other as well, sure, following the same principle, similar principle.
Anybody?
So the question is that when we talk about the electromechanically induced transparency, and one is the optomechanically induced transparency, then we also create a transparency window for the probe field. Like in optomechanical, I want to say like, is it kind of a transparency of the mirror that what involved in there for the incoming photons?
Okay, so you want to say that the mirror,
Maybe it is transparent or not, that what it is.
well, you see, once we say it is induced transparency, so if we discuss the induced transparency in our conventional quantum optical way, so then we say that the medium becomes transparent. So if we have a probe field, it passes the medium as if there was no medium. Fine. So here we have we are experiencing this, we are observing this in the presence of movement of the mirror. So what we are saying that the moving mirror presents a prototype of the medium. So it has the same behavior. So now it is not the mirror which is transparent, rather this probe field, once it's passing in this arrangement, experiences a transparency window as if there was no end mirror, moving mirror, and so on.
So is this system is purely quantum mechanical or can be semi-classical?
Well, here we have is quantum mechanical system.
And what about these 6 dimensions you talked about? When we add atoms and nanoparticles and that everything.
Okay, these are generalized coordinates, because once we have once for one particle in one dimension, we require two generalized coordinates, position and momentum. And if we have two particles, so we require four dimension space in one dimension, position and momentum for one particle and position and momentum for the other particle. So it's four dimensional. So in that sense, if we add one more particle and we want to see the dynamics, so it should be six dimensional.
Okay, thank you so much. Let me check it from anybody else have a question? The question that is by the Miss Sadiki, and he is asking how the intrinsic, I don't know how to pronounce this, can be controlled while designing desired optical field and cavities. That is the question.
Let me.
Yeah, sure, you can check it.
So the question is how the intrinsic ambiguities can be controlled while designing desired optical fields and cavities. Well, now, what do you mean by intrinsic ambiguities? If you say that it is the noise or it is the, if you want to say this is the, okay, I would say that please explain your intrinsic ambiguities, then I can answer this.
Yes, please, Mr. Sadiq, if you are online, please repeat your question. Okay. Okay. So there's a lot of students who's asking for your slides. They want your slides. So if you so what's the procedure for that? How you take?
You have my slides, so if you think
Yeah.
you can give.
Yeah, okay. Because we also received the emails. Okay. Maybe we wait for Mr. Sadiq. He's saying yes, noise.
Okay, well, we can include noise in in our calculations here, and that is sometimes helpful in understanding various different characteristics of the system. So in our work, we can include noise that is as it is there. Yeah, thank you.
Okay, thank you. Okay, thank you. So today is the fourth day of our lecture, and tomorrow we have the fifth day of the webinar. That is the last day of the webinar. So if you have any question regarding sir book, related to sir PDF, related to sir work, regarding research work, you can ask from sir by like 2:30 p.m. from the webinar series at the end of webinar series. And the certificates, about certificate, we are giving the certificates those students who have a 80% participations. It's our very strict rule from now that, so please, you must have a 80% participations. So thank you so much, sir. Thank you for your time, and that's your very guidance, very insightful lectures. Thank you. Okay, so join us for the tea break, please. Thank you.
Online hostel. YouTube channel.
Okay, those who are asking about the video lectures, these are available in our YouTube channel, Comstech YouTube channel. You can go and check it from here. Thank you.